my name is Nicholas Stone, and this is my Lab 1 report. The purpose of these labs are to showcase my understandings of fundamental physics concepts, and in this case, it's kinematics. I will be showing an object moving along in real life along the x-axis in the same direction without changing speed. And in order to do this, I will be using the provided GlowScript template, as well as Newton's second law, F equals ma, the idea that the net force is zero, which essentially allows us to simplify the following kinematics equation, that the new velocity will always be equal to the old velocity because the net force is zero, and finally the updated position equation, which allows us to calculate future positions through the addition of the velocity and the time. I recorded myself rolling an empty Celsius can across my smooth dorm floor. An empty Celsius can which has an approximate diameter of 5.7 centimeters and an approximate mass of 15 grams. I then created a point mass to find the position for each of the 17 frames, and you can see this over to the right. Below the x-axis graph, we can see our y-axis graph, which is not relevant to the purpose of this experiment because it's showcasing the difference in height, which is just error on my part for not being as precise. However, we can go ahead and see all the data points in this table right here, and we can use our formula to calculate our average velocity, or our perceived average velocity, by taking 2 points right here, subtracting one from one another, and then dividing that by the change in time right here, which should give us an average velocity of 0.83 meters per second. So that's how I recorded my observed data, but let's see how this compares against my predicted data. Utilizing the following GlowScript file, I went ahead and changed the following. I made our initial velocity 0.83 meters per second, which we just calculated. I made our net force equal to 0 because we're assuming a constant velocity, and I finally put in our two equations which we just talked about, which is our updated velocity formula and our updated position formula. When we run this program, we can see what our idealization looks like for a constant velocity of 0.83 meters per second. As you can see here is our constant velocity, and here is our slope representative of our constant velocity. Let's compare these two data sets. I compiled each of the positions for each dataset into a txt file particularly formatted, and then created a Python script which read the data in this format from each dataset and created a graph using matplotlib to showcase the two datasets alongside each other. Our final output shows something very interesting, that the two datasets do not line up as well as initially hypothesized. As you can see, the predicted dataset showcases our idealized 0.83 meters per second squared. However, the observed dataset shows that there is clearly a less steep slope, which indicates a much lower average velocity. Though it shows a generally linear trend, you can see that it is not as smooth as our linear predicted set. So what does this mean? Though the datasets were relatively close to each other, they were still pretty different, and that means that there are some potential sources of error in our experiment. Number one is that friction exists. As I was rolling the Celsius can across the floor, it tended to get slower as it went on further because of more friction that was acting upon it. Number two is likely the human error that was made when I was measuring each of the points. Because I didn't have a defined system of where to place each of the points for my data point, it's very clear that if we get into the minutiae of things, that the measurements could be ever so slightly off. And finally, I only tested on 17 frames for this video, and because there is such a relatively short amount of frames, that even if there was a potential source of error, that was it was particularly espoused by the fact that there were such short frames. If there were larger frames, it's likely that the average velocities might have become more homogeneous. Now let's answer the following questions. What if we were to flip the axes, such that we interchanged positive x and negative x? There would be no difference in the data except for the signs. There would be no difference in the relative position of where the object is moving except for the fact that it's just going in a different direction. Additionally, the average velocity that we receive would not be any different in terms of its magnitude, but in its direction it would be the opposite. Next, is it possible for us to say how many pitches and pulls are being added together to give zero net force in the case that you observed? The answer to this is that If we have zero net force, it means that it does not mean that there are no forces acting upon it. It simply means that the sum of all the forces equal out to zero. And this is likely the case we receive such a big difference between the observed and predicted data in the final output, because of perhaps the push that I gave on the Celsius can or the friction that it was interacting with on the ground. That likely means that the addition of those forces gave a net force that was not equal to zero.